Hi everyone, welcome to this video on lesson 15 of atomic structure and periodic table. This one is on the noble gases. So we've been looking at the reactivity of group 1 metals and the group 7 gases, the halogens, in the previous two lessons. In this lesson we're going to look at the unreactivity of the group 0 elements, which are called the noble gases. And this is one where I think it's helpful to kind of teach a little bit through the examples and get students thinking about how our abstract pictures to do with electron configuration and so on help to explain things actually in the real world. And it might be a surprising place to start, but what you can do to begin with is draw a bowl, and then you can draw some crisps in there. So here's some crisps like that. And what you can do is say, well, what happens if you leave a bowl of crisps out exposed to the air? And students should be able to tell you, this has probably happened to them at some point, that they kind of go a bit soggy. So I don't know how to draw soggy or soft. Not soggy, that's the wrong word, soft. They lose that crunch. I don't know how to draw crisps that have lost their crunch, but you can just label these and say they're soft. Now, what we want to do is explain why that happens. So why does that happen? Well, that's because if we zoom in on here, the reason crisps lose their crunch is because if this is our crisp here, exposed to the air, what happens is particles of oxygen, or atoms of oxygen, I should say, come and react with the my guess is, I've not actually looked this up, but my guess is it's with the oils in the crisp. I'm going to just get rid of that arrow and do that in red because I've been doing that in the other lessons. But there's some sort of reaction between oxygen and the crisp, and it's that reaction that makes the crisps go soft. This is what we want to say to students. So because you get a reaction here, the properties of the crisp change, and therefore we get soft crisps. So what we can explain to students is what happens inside a packet of crisps. So inside a packet of crisps, I'm not going to attempt to draw walkers here or anything like that, but you might want to say, here's our packet of crisps, something like this. What happens is this packet, before it's sealed, is pumped full of argon. Now, if we draw our crisps inside here, you'd hope you get a few more than that, although with inflation and everything else, maybe companies are starting to cut down. But if this is our crisps inside our packet here, and the packet's been pumped full of argon, well, we can look at what's going on here. If I zoom in on here this time, move that down so you can see. Well, if I look here at an argon atom, like this, so that's AR, I can zoom in again and say, well, let's look at this argon atom. And this is where there's some whiteboard questions where students are asked to draw the electron configuration, so then we can come to this in our explanation and say, well, look, my argon atom has this configuration 288. It's got an atomic number of 18. So I'm going to draw my 18 electrons here. So again, we're going from concrete to a little bit abstract to even more abstract. Now we're looking at the electron configuration. And the point that you want to raise to students is that actually, because this has a full outer shell, it doesn't need to react. It's not going to be interested to kind of anthropomorphize this atom. It's not going to be interested in what's going on with the atoms in the crisp. So there is no reaction. Because this has a full outer shell, it's super unreactive, and therefore there is no reaction between the argon and the crisp. So if I draw a few more argon atoms, what you want to emphasize to students is that whereas the oxygen reacted, and again, looking at it now, perhaps I should have zoomed in on the oxygen and showed that because oxygen gas only has 6 in its outer shell, it maybe wants to gain 2 more, and it can get some of those from atoms inside here. we maybe don't need to go into that much detail. The point that you want to make is that full outer shell makes this unreactive, therefore the argon doesn't react with the crisp, and therefore if we go back to the concrete again, I'm just going to draw my, let's try and draw a crisp packet a bit better this time. Something like this, if this is my pack of crisps like that, with my not many crisps inside. The point is, and again, I don't know how on earth you draw this, but maybe just the label is fine, that these inside this argon filled packet will remain crunchy or crispy. I don't know whether are crisps crunchy or are they crispy, I don't know. Anyway, hopefully that illustrates what the point that we want to get across. And if students can explain that and say something along the lines of, if the crisp packet is filled with argon, then because argon is unreactive, there is no reaction between, there's no opportunity for reaction between oxygen and the crisp, and therefore the crisps remain crunchy, then we're helping them explain some really concrete things in terms of these more abstract ideas, which is really what our job is all about. We could do another one here, although I think I might not go through it in this video. I'll just post an example diagram to share in the slides. But we could do a very similar thing with the reason we fill light bulbs full of argon again, and that's because we don't want the oxygen in the air to react with this very, very, very hot piece of tungsten metal because it would combust. The reaction between oxygen and metal is combustion. Students have seen that with magnesium. You do get a really bright light, but that would lead to us breaking a lot of light bulbs. So we pump that full of argon because even when that tungsten metal is super, super, super hot, and it would react with oxygen just like that, if we pumped it full of argon, because argon is so unreactive, it's not going to react, and then we can keep on using it again and again and again. In the next video, we will be looking at transition metals.